From the information we have here, at time equal to half-life, we know that the amount of the nucleus at that time is equal to the amount of the nucleus at the initial state divided by 2 or reduced by half. And from the rate law equation, we know that the dN by dt is equal to Kn. This is the first order reaction. So n here has power of 1. Okay. So to find the K value or relationship between the K value and the T, we have to change delta T to be T, right, by integration. So what we can do is change the form of this differential rate law equation to be integrated rate law equation. So I move things down. So we have 1 over n dn equal to k dt. So after that, we can then integrate both sides. Okay. So integrate of 1 over n here, but we have to integrate it between the range of time from t equal to 0 at the origin to t equal to t. Okay. And this is n equal to the original n and n at nt. Okay. So with this limit of time, after integration, 1 over n dn is equal to ln n, right? So it is ln n. But because we have the time range over here, so it have to be nt divided ln nt minus ln n0. But we have minus on top here. So we have ln n0 minus ln nt. So it is equal to ln of n0 over nt. Okay, we have this one. And on the right hand side, we have integrate of k dt will be equal to kt. Okay, and we have the limit time limiting. So we have kt minus k multiplied with 0, which is equal to 0. So we have kt, just that. So I move it to the right a bit. So we have ln of n0 divided by nt equal to kt. That means if you know the amount of the origin, amount of the final at t equal to t, then we know that how long it takes to decompose this amount of radioactive isotope. Or if we know t, then we can know the amount of the radioactive isotope remains from this kind of decomposition. So now because we know that at t equal to half-life, then nt will be equal to n0 over 2, right? So we use this one and then substitute here in the equation. Because nt equal to n0 divided by 2 and not divided by 2, so it is actually equal to ln2, right? And this is equal to k multiplied with the half-life here. So from this, if we want to know the rate constant of carbon-14, then we can calculate it from the half-life of carbon-14. So we move the half-life down here. So we have this. So we know the K value of the decomposition. And if we know the K value over here, we can then calculate the rest of the thing. So actually, from this equation, we can also make it like this: NO over NT equal to E, and then with the power of KT. But the power of KT is equal to ln2 divided by half-life, and then multiply with T again. Okay. So if we want to know the amount of things, okay, left behind in the specific time, we put T over here. If you know the rate constant, if you know the half-life, we know the rate constant, and we can calculate things. Okay, so we can swap the place for the variables and change form from the logarithmic function to the exponential function, thing like that. Okay, so now my question, the first question is find the rate constant of carbon-14. So we're going to use this one and then we find the K. So the K is equal to Ln2 divided by half-life of carbon-14. So the K unit of K will be equal to the unit of half-life that you're using, right? You can use whether second, minute, whatever, right? So I will use year. I'm not care about the SI unit anyway. So we have this. So now we can find the K, which is equal to, let I use my calculator. Where's my calculator? Okay, so it is Ln2 and then divided by 5730. So it's 1.21. This is 1.21 multiplied with 10 over minus 4. And the unit is year, reciprocal year. We have that. This is the K value, okay, which is the answer of the first question. So after we have the answer of the first question, we can work with the second question, how old a piece of wood, right? A piece of fossils of wood, which is contains carbon-14 just at 8%, comparing with the normal carbon-14 found in the living wood. So we have many equations over here. You can use whether this one or this one, whatever, because we know everything now. It's up to you. So I will use this one. Right? We have calculator. We can use logarithmic function. We can use exponential function, whatever. So Ln of the original state. Original value of carbon-14 is 100, right? Before decomposition, it decomposes and left just only 8% after decomposition. So NO, N0 is 100, NT is 8. And then it will be equal to KT. So the K is that 1.21 multiplied with 10 to minus 4, right? And then we have T here. So T calculated would be in year because the K value here is in the reciprocal year unit, right? So that's it. So I have to use my calculator again. It is the Ln of 100 divided by 8. Ta-ding. And then again, divided by 0.121. So it's 20,000 something year. So the T is equal to about this 20,000 year, 21,000 year. So with this kind of technology and the knowledge of half-life of specific radioactive element, we can find the age of any kind of fossils. But you have to beware choosing the right element to be calculated. Because if the fossil, you think about the fossil that may be in the age of billion years, almost many million years, for example, the carbon-14 will be left in that kind of fossils too low, and we have no sensitive enough things to find the carbon-14 content in that fossils. So we have to change from carbon-14 to some other things, like potassium-40, which has the has the half-life of potassium-40 is about 1.2 million years, things like that. So it have to select the right radioactive elements that can be found abundantly in that kind of fossils. Okay. So it depends on the objects that you want to find, the age, and yeah, the age roughly. Okay, what is the age roughly about that kind of fossils? So select the right thing to do the radiometric dating. Okay, so this is how we can make use of the knowledge about nuclear chemistry. Okay, so next, what we already talked about is just a particular nucleus decomposes with so many kind of mechanisms, things like that. So next topic, we're going to look at the reaction of the nucleus. So the nucleus is not auto decomposes, but we're going to react the nucleus with something else, okay, in the next topic. So see you again in the next video clip.